Good morning, everyone. Welcome again in this physics class of magnetic field and earth magnetism. Children, firstly I will explain syllabus. A current loop or as a magnetic dipole, its magnetic dipole moment, a revolving electron, magnetic field intensity due to a magnetic dipole, bar magnet or axial line and equilateral triangle. Torque on a magnetic dipole bar magnet in a uniform magnetic field. Bar magnets as equivalent solenoid, magnetic line of fields, and earth magnetic field and magnetic elements are in not my course. Children, number one point I will explain current loop as a magnetic dipole moment of a current loop. Similarly, firstly, I will explain torque because in this chapter, magnet or current is depend on the area and magnetic field and force. So, children, we know that about the torque, that is the turning effect on the body about an axis, is due to the moment of force or torque applied on the body. Children, a current carrying solenoid or coil or a current loop behaves like a bar magnet having north and south pole. Children, north and south pole. It is the north pole and south pole at the ends of magnetic dipole, and so the current loop is also magnetic dipole. When a current loop is suspended in a magnetic field, it experiences a torque, very important point, torque, which tends to rotate the loop to a position in which the axis of the loop parallel to the field. Children, the magnitude of the torque acting on the current loop in a uniform magnetic field with the axis, very important point. Children, listen, very important point, learn it. That is torque equal to IAB sin theta, where A is the area of the current loop and I is the current, B is the magnetic field, and sin theta is an angle between the magnetic field and the coil. Where A is the area of the current loop. We have read in electrostatic an electric dipole placed in the electric field also experience a torque which tends to align the dipole along the field. The magnitude of the torque acting on an electric dipole in uniform electric field with axis at an angle theta with the direction E vector is given by torque is equal to PE sin theta. We know that torque is equal to IAB sin theta from chapter 8. That is torque on a current loop moving coil galvanometer. And in this chapter or formula, that is torque is equal to PE sin theta, because PE represents the dipole and E represents the electric field and sin theta represents the angle between the force magnetic electric line and the charge. Children, where P is the magnitude of the electric dipole moment. Okay, children, so comparing equation first and second. Then we can associate the magnetic dipole moment with the current loop of the area is equal to M equal to IA. M equal to small a, M equal to IA, where SI unit of M is the ampere meter square and its dimension is equal to AL square, because I is the current and A is the area. Dimension of A is the A and area is equal to L square. SI unit of M is the ampere meter square, because I represents current, that unit will be ampere, and area represent length into breadth, that is meter square, and dimension are AL square. Okay children, the magnetic dipole moment equation is written in the vector form, that is M vector equal to IA vector. Very important part, the M vector is equal to IA vector, that is 2 marks in ISC council, where A vector is the area vector perpendicular to the plane of the loop. Thus the direction of the magnetic dipole moment is perpendicular to the plane of the loop. Children, we know that the formula of the magnetic moment by the help of current loop as a magnetic dipole. Children, next we know that consider a current loop is equivalent to the magnetic dipole if area of circle is the pi r square, that is M equal to IA area of circle, that is A square. Children, circle is that and radius is equal to A, right? Radius equal to A. So area of circle is equal to pi A square. Therefore, I equal to M upon pi A square. Equation number 3. But the magnitude field at the center of the current carrying loop in terms of current through the magnetic field in current carrying loop at the center of loop, that is B equal to mu 0 I upon 2A, where mu 0 is the permittivity in free space, and I is the current, 2 is the constant value, and A is the area. This is equation number 3 and 4. The magnetic field B at the center in terms of the dipole moment M would be, that is B equal to mu 0 upon 2 pi M upon A cube, that is B equal to mu 0 upon 4 pi into 2M upon A cube. Children, after solving that, we find the value of M vector equal to NI vector. M vector is the dipole moment, N is the number, and I is the current, A is the area vector. Okay children.